Cool. Right. So I received some questions via email that I am going to address, but I'm first briefly going to go over these slides, and I'm going to ask you whether you answered my questions. Right. So I'm going to zoom in a little bit. My word of warning is the balances we are going to solve is the mole balances. Mole balances, mole balances. There is not a thing like a concentration balance. When my suggestion to you is when you solve stuff in Python, start with your mole balances and solve for FA. Or in a batch reactor, solve for Na, and then after you've solved it using solve IVP, it is very easy to afterwards get an array of values for your Fa, and then to quickly calculate an array of X values, an array of concentration values. Why do we want the concentration? Why are we so stuck on when we write mole balances to translate it into a concentration? Can anybody tell me? Why do we want concentration in our mole balance? Anyone? Typing or words? It's easily measurable, right? Okay. But why do we need it? A flow rate is just as measurable. Information we give to the clients, concentration, yes, it's an important variable, but more importantly, what we want to give to our clients is I am going to make you X moles per second of this good stuff. And I start with Y moles per second of this bad stuff. Right? So concentration is not really a variable that you're going to report to your clients. Why do many textbooks and many people who write to solve the stuff analytically? Why do I write? There we go, Sean. The rate constant. And we need concentration in the rate. So this is the conundrum here. We need concentration because we want our rate, because that will be a K times a concentration or whatever. But remember, concentration we can always calculate using an algebraic equation as your molar flow rate divided by your volumetric flow rate. So for each step, as you are integrating over a PFR reactor, this is part of your algebra. This is part of the algebra when you are solving your rate equations. So you just have an algebraic equation, you integrate over molar flow rate. You solve for molar flow rate in a CSTR. And in your solver function, you will have a sub-calculation where you calculate concentration and where you calculate your rates. This is just my word of warning. Concentration, I'm going to catch you out if you try to do concentration balances. Right, questions on that? So we're going to practice this in all the TATs. Stay away from concentration. Calculate concentration in order to substitute in your rate. Right, questions on this? Clear my screen. Okay, so now if we move on to this last part of my very important, we are going to introduce even more rate bases as we progress through this course. So just to be clear, when we have no specific accent there, it's a volumetric base and it's per volume reactor. And when we have a little dash there, we want to calculate it per kilogram catalyst. So this is per kilogram catalyst that I have in my reactor. Are you used to that format of writing the rate equation? Just a few yeses or nos, please. Yes, right. So you're familiar with that. Are you familiar? So now, please, anyone. So in a CSTR, we use the packed bed density. So units, kilograms per cubic meter reactor. That's the packed bed density in a PBR to convert between the different unit systems. So if I will always have one independent variable. My independent variable can be along the length of a packed bed reactor. It can be mass of catalyst. It can be the volume of the reactor. It can be the length of my reactor. And I need to Then for my independent variable, I see how my dependent variables, which will be my molar flow rates for now, changes along this length. I need to be able to translate my equation so that if somebody gives me a rate equation on a per length basis or a per mass basis, but I want to do my balances with Z as my independent variable, I need to be able to translate that unit system. Right? So now, after all my scratchy-watchy, please, can you answer this question? Can you answer this question? What must be in that block? So let me just set the scene. You've got a packed bed reactor with a specific diameter. And it's packed with catalyst particles at a certain density, at a certain packed bed density. What must I use there in order to get my units to have length along the reactor as my independent variable? Can anybody answer that question? Shall I give you a minute or two? Are you still there? Mass catalyst divided by the length of course. So she is correct. What we need is something that has got units of mass of catalyst, which will give me kilograms per meter. So that is the units that I want, okay, per length of bed. But I need to key that into the physical dimensions of my bed, stuff that I can measure. Stuff that I can measure. So you are on the right track. I want that, but I want it in terms of measurable or known or qualities of my bed, properties of the reactor, dimensions that I will know. How will I calculate the mass of catalyst per length of bed? Yes, Philip.
Can't you set up a differential equation like, say, something like dW is equal to the rho B times the A cross-sectional area times dz, and then use that?
Okay, so, all right, so what he wants to do is he wants to do remember, you are already dividing by dz. Packing density, yeah, Angelo says packing density times the area of the bed. So we've got a density of the bed divided by the unit area of the surface, and then I've got to multiply by, which is fantastic. I've got lots of incorrect answers and some correct answers, right? So now, this is something that is so easy, but that will trip you up for the rest of the semester if you don't figure this out. Don't figure this out. So let's just get a whiteboard. Let me just get a whiteboard. And let's write this down. So we want something that has got units of mass of catalyst per length of bed. So it must have units kilograms per meter bed. So first off, if I want the mass of catalyst along the length of my bed, so let's just say there I've got my bed and I've got a little slice over there. So I want to integrate now over this little slice. Okay, so I want to know in this little slice, how much catalyst is there in that little slice? So of course, I'm going to use the bed density, and then I have this cross-sectional area. So let's just say we're going to have the volume of that slice. Density times volume will give me the mass. You agree? Okay. So if I have the volume and I want to write it in terms of dz, of course that will give me, now yeah, green is a bit light. Let's go black. So if I have the bed density times the cross-sectional area, which is just that, which of course is equal to pi d squared divided by 4, where this d is my tube diameter, right? Multiplied by dz. Are we in agreement? Can I just see some proof of life, please? Josh, yes. Josh, did you have a question or are you just saying yes? Right, so you all agree with me. So this will give me the mass of catalyst, but I want to have, what's the mass of catalyst per bed length? No? So fantastic, look there, that cancels out. Right, so the factor that I actually need is just the bed density times the cross-sectional area. Because if I look at this units, so I don't need a new differential equation because dFA/dz already, right? It is per meter. And this is all I need in order to get this per meter. Okay. How does that feel? Are you comfortable with that? You're going to do this kind of calculation for other kinds of unit bases frequently throughout that course. Any questions? No questions? Right, so let's just go back to our slides. Cool. Right. No questions. Okay, so then we are going to, okay, for a CSTR, what is the units? What's the across? Just the, exactly. So the cross-sectional area gives me the volume. And if I multiply that cross-sectional area, the volume, that small little volume, by the density, I get the mass that is in that little slice. But I want to divide that by dz because Lisa correctly said that we want the kilograms per meter, and then that dz term just falls away. Right. Okay, so what's the units? What's the variable that I need to convert? So let me just get a red pen. If I want to convert mass over here, like this is for a packed bed reactor. If I want my independent variable to be volume, I have to take my mass based rate and multiply it by the bed density. So for a CSTR, if I have my rate in a mass basis, what is the thing that I must multiply it with in a CSTR to get it to a volumetric basis? Let me just check. Answers, please. Ching, ching, ching. We'll wait. What is the thing?
It's the catalyst concentration.
Thank you very much. Very brave. So that's definitely, so in a CSTR, I don't have a packed bed density. I have, what is the amount of catalyst that I have per cubic meter reactor? And that is the catalyst concentration. So now, be careful in this subject. We are going to have stuff with similar units. So if you now look at this, catalyst concentration and bed density, it's got exactly the same units, but it says something quite, the one is a density, how much is packed in that bed. The one is in a CSTR, we refer to catalyst concentration because it's something that is floating around in a liquid phase or it's fluidized in a gas phase reactor. Right, so happy with that. Let's continue to our next slide. While I'm erasing, you can raise your hands or type some questions. Okay, right, so X conversion. I am sure Dion or Dr. Brink tested you on this, is be careful with conversion with X. It is always based on a molar flow rate. So if I want the overall conversion, I will use the molar flow rate out relative to the molar flow rate in. In some of the TATs and the online tests, what I'm going to do is I'm going to separate a stream off here. So, okay, this is now, I take off a little bit here. Please calculate the overall conversion. Always relate what is the truth and the only truth, not conversion, not concentration. What is it? What's the variable, the dependent variable that will give us the truth?
Flow rate.
Okay, so this is which flow rate? The molar flow rate. The molar flow rate is the variable that gives us the truth, right? Because it cannot lie. It doesn't want to know whether it exited from reactor 1 or reactor 2. Okay, so if you want to calculate conversions, please keep in mind for conversion as well as concentration, molar flow rate is the variable that you relate to. I can calculate the conversion. Yes, this is a mess. I can calculate the conversion, just incremental conversion, just over reactor 2, just to find out its performance. Let's say I'm busy optimizing this reactor. And I want to do it with conversion as my goal function. I want to optimize that conversion. Then yes, I calculate the conversion relative to that inlet flow rate. But if I want to finally find out if I now want to sell it to my customer and say, yes, I've done a good job, I will use the overall conversion over this entire system. Right. Be careful with conversion, but we will get some tuts where it's going to trip you up if you don't concentrate on doing mole balances and calculating conversion relative to the correct basis. Right. Levenspiel plots. Yeah, my first tut is, of course, one of my favorite people is Professor Octave Levenspiel. Such a cool name, Octave. Octave Levenspiel. And this is a very handy way of representing data. I'm sure that you are familiar with the Levenspiel plot. So I like to present my Levenspiel plots using as my independent variable. So now, if you ask me, okay, let me ask you this. Do I draw a separate plot for Levenspiel for whether I am busy with a PFR or whether I'm busy with a CSTR? So is this a legitimate question? Is the Levenspiel plot for a CSTR or is it for a PFR? Do you think that is a legitimate question? Let's give a poll. Poll, yes, start. Poll it. Is that a legitimate question? Okay, I'm going to give 5 more seconds. 5, 4, 3, 2, 1. Okay, right. So I'm just going to show those who voted. So there are some yes and of course some no answers. The true answer is Levenspiel plot is blind to your reactor type. It is actually just a representation of how your rate changes with a conversion. So with the conversion, and now we might say it's just concentration, and in your lives when you did what's that subject, CKN? It was just to say, if I have different concentrations, how does my rate behave? And I always will start with what I feed to my reactor. And it is blind, completely blind, ching, ching, to the reactor type. Okay, so you construct a Levenspiel plot by saying, how does the rate change with concentration? I like to use X on my plots because then it goes from 0 to 1, whereas concentration will go from, this is where I go into my reactor and go in the opposite direction. And I am not Hebrew, so I'm not used to writing in reverse. But, you know, some people can translate their brains to work like that. I like to start at 0 and I like to go to an endpoint. Another beautiful thing about X is that we know its boundaries. It starts at 0 and it can only go to 1. Whereas concentration, you know, you may have to think about your boundaries. So I like to set up an array of values for when I construct these figures. For my X value, don't start at 0 because since we divide by that RA, don't start at 0 and then later you will see that you may divide by a 0 term later on, and also don't go to 1. So start at 0.0001 and go to 0.99999 in your arrays. So for each X value, I can calculate my concentration, I can calculate my molar flow rate out, I can calculate my concentration, I can calculate my rates, and I can then construct my figure. Later on, when we bring in the energy balance, for each X value, my temperature is also going to change. And that is going to affect my rate because rate is very temperature sensitive. Right, so you have an opportunity of practicing your Levenspiel plots in that one. So just what does it represent? I always use my mole balance for the CSTR to just say FA naught times X, if I have a single reaction, is equal to minus RA times the volume of my reactor. So for a CSTR, you all know that if I just take this little block, what am I doing here? I am multiplying 1 over minus RA with X. So if I just reshuffle this, 1 over minus RA times X will give me the volume divided by FA naught. So this area that I have is the same as this volume divided by FA naught. Okay? And I can, of course, write this in terms of a concentration if I want, and the volumetric flow rate, which results in this residence time concentration issue. Right? But I'm normally, and this is a good question I had via email, I'm interested in sizing my reactor. This is what it's going to be all about in this course, is what is the volume that you need for that reactor? And how am I going to shape that reactor? How will it look? Will it be in tubes? Will it be fat? Will it be thin? So you've got control over how that reactor looks. But first off, you will use to find that volume. So the question I got was, where do we use the residence time, this tau, the residence time, which is volume divided by Q? Where do we use that? Does anybody have an idea of where we use that? Sorry, and now I require you to wake up and type. Leave your phones. Get off your, stay on your phones if you're watching this on your phone. Stop texting your friends. Where am I going to use? What is the benefit of representing a volume in terms of a residence time and not just a volume and a flow rate? Anyone who's got an idea? Tring, tring, trick, trick, trick. Cool. Silence. If you've got no idea, just type no idea. It explains how long it would take to get the product. So yes, optimization, nope. Optimization I can do with volume, but thank you so much for answering. I can do it with volume. So I can say, mass catalyst is, I can get less catalyst, and less is not always better because there's another price that you may need to pay in terms of the operating pressure or the operating temperature. It takes an idea of how long material takes to go through the reactor. That's all good. But why do you need to know that? Batch reactor. Okay. Why do you need to know for a batch reactor? Okay, you are right. It affects the heat balance. I can do an energy balance and not think about a residence time once. Not once. Residence time, right? So why is residence time important? First, we can make is it feasible? Time is money. Time is money. What you are going to do in the end when you design a proper reactor is to say, this is how big this piece of steel must be. It has time to transfer it, design. Okay, yes, you are all of course correct. But when we design the reactor, we are not going to design for residence time. We are going to calculate the mass of catalyst, volume of our reactor. But what this residence time does, it is a scalable factor. It is a scalable factor. So what do I mean by that? Somebody works in a lab and he's got a teeny weeny reactor. So teeny weeny reactor with a teeny weeny volumetric flow rate, so the volume, and then he's got a certain residence time. Somebody wants to repeat this reaction on a bench scale or a pilot scale. So at least he's got a scalable factor that says, okay, so if I now want to change this volumetric flow rate to something bigger, so let's just make it bigger, to something bigger, in a bigger reactor. How bigger must it be? And then the residence time gives you a good scalable factor to translate between different size bases. It also gives you a reasonable person, so you can go in literature and say, typically, these kinds of reactions require a residence time of that. So it gives you a starting point for your design. Residence time, or we are going to use something like the weight, hour, space, velocity. It gives you a starting point for your design, heuristics if you want, to compare to typically what is in literature, what does it say? How long does this reaction need? And then the detailed design, we will go to volume, mass of catalyst, detailed for your specific design. Does that make sense? Questions? Are you happy with that? It's a scalable factor. Yes, you were all correct in that it says how long the material must stay in there. But for a specific reactor type, if you just have lab scale measurements, it's easy to, when I evaluate the design projects at the end of the year, I look at the kinetics and I look at the kinds of reactors that were sized in the papers where they published the reaction kinetics. And I calculate typical residence times. And I say, all right, okay, this is more or less the order of magnitude. That's all it says, the order of magnitude of how big your reactors must be, just to get a feel for that. Right, so it's a scalable factor. It gives you a reasonable range. Is it the same? SCFH. No, you're going to have to help me with that. So it's some more typing needed, Nico. Look, we're running out of time. SCFH. Just type what you mean. Standard cubic. No. Standard cubic feet per minute is a variable that measures a flow rate. Right. So this is a unit that's got a specific volumetric flow rate in a sized reactor. So it's not like that at all. It is for a specific reaction. How long does it take to complete? And therefore, if I start sizing my reactor, I need a starting point to say, okay, try a mass of this, just to get me started on my design journey. Right. Okay, so thank you very much for that question. Our last slide is, of course, for people who love thermodynamics. It is the favorite slide. And this has to do, so I'm going to be finished in a bit. So I know that you are booked for 2 CRO. It's not going to be this long normally. So if the exo and endothermic reactions, I had another question on this. And this question was the rate of these reactions. Will they always be elementary? So will it always be KCA minus K over KCB? Will reversible reactions always have an elementary rate equation? And unfortunately, the answer is no. Because the rate equation, what you must understand about the rate equation, it is not a law. It is somebody that goes into a lab and they measure for a specific concentration range. They stir and they measure what happens with the concentration with time, and they try to come up with an equation that fits their profile. So they model it. It's like somebody doing a CSC project to say, how fast will this happen? And there are certain guidelines. Yes, first try elementary. But then if it doesn't work, try to say, oh, but some of it is absorbed on the surface, and then I've got a very funny concentration that I write there. So no, it is not always elementary. You need to follow, and also when people publish rate data, they've got a specific range of temperatures and concentrations for which their rate expression applies. It's not necessarily true that that rate expression applies to all kinds of ranges. So if I now, for instance, increase my temperature to be 10% higher than the temperature range in which this guy did his experiments, his rate equation may not be applicable anymore. So please note that you should rather see a rate equation as some kind of empirical equation people came up with. So we can't say that it's always looks like that or it always looks like this. People have been very creative when they try to come up with equations that fit their data. Right, so that question, I want to, so this, I think you are all sorted. We will practice this, in specifically if you do your Ergun equation. Work through this. If you've got more questions on this, I will going to stay on the line. I will close the recording and stay on the line. So we're going to finish up with this equilibrium part. We are going to explore this later when we bring in the energy balance. And seriously, our power, we are powerful when we design reactors. Our power of manipulating the temperature of controlling and specifying the temperature in our reactor, or in a PBR, the temperature profile over our reactor, affects the behavior of my reaction, right? So now, for an exothermic reaction, if I have warmer, let's say I build in even a warmer reacting system, even warmer. So let's say I operate at 300 degrees. Exothermic reaction will have lower possible conversion. That is a law. That is the combination of the first and second law and the Gibbs free energy minimization that tells you this is where this reaction will stop. It will go there extremely fast. This is the conundrum. It will go there extremely fast and then it's just going to stop, right, for an exothermic reaction. And that is what we must manage when we design our reactors. We want something fast, but we don't want it to go nowhere really quickly. So we need to optimize that balance for exothermic reactions specifically, is how far can my reaction go and how fast does it go. So this was a really fast on reversible reactions. We'll revisit that, but let's just see if you could answer my question. So if I now add this reaction, which is obviously, is this exo or endothermic? This is obviously exothermic. Why? Because at higher temperatures, I get a lower K equilibrium value, van 't Hoff. Lower K equilibrium value, and therefore a lower maximum conversion of reactants to products in my reactor, right? So now, if I now say, let's just start with B that goes to A. So I have the reverse and I feed pure B to my reactor, right? And I want you to redraw this figure for two temperatures. Temperature is 100 degrees and temperature is 200 degrees Celsius. Okay, so I'm not going to ask somebody 100 and 200 degrees Celsius. How will that figure look? So I'm just going to open a blank board and I am going to give you, just take a minute to see if you can come up with that figure. For an endothermic reaction, how will it look? So now, I wonder how many of you are actually attempting this. I wonder whether I would, if I were in the audience. So I want you to draw A versus time. So this is in a batch reactor. B goes reversibly to A. It's an endothermic reaction. And I want you to draw it for, oh no, sorry, shucks. You can't delete just certain sections. So while you're busy drawing it, temperature, B reversibly goes to A. It is endothermic. And I want you to have a temperature of 100 degrees. We want to draw that in blue, and a temperature of 200 degrees, and we want to draw that in red. Right. So have you figured it out? So for an endothermic reaction, it is going to go faster, rate equations, always faster, the warmer. The warmer, the faster, the rate equation. Arrhenius, your activation energy, always a positive value. So here I'm going to have the 200 degree one. And for the 100 degree one, it's going to go slower because Arrhenius, initially, Arrhenius, how fast does it go? And where will it go? It will go slowly nowhere. Right, so I have a lower equilibrium constant at 100 degrees, and I have a higher equilibrium constant because my del H reaction has got a positive value for an endothermic reaction, and we are going to explore van 't Hoff in order to see how our equilibrium constant changes with temperature. So for the endothermic reaction, are you still there? Do you agree with my figure? Do you have questions on my figure? Proof of life, please. Of course. Thank you. Yes, you are correct. You don't agree. You are wrong if you agree. Yes, because this should be CA. I'm forming CA. Yeah, you are all agreeing too fast. That was an intentional slip of mine, of course. Right. Okay, so I am going to stop the recording. For those who still have questions, or maybe we will have an after class Q&A session recording. Let's just stop this.